Hello, welcome to Shine Sleep Stories. Close your eyes for a moment, relax your shoulders, slow your breathing. Right now, you have nowhere to go and nothing to do. The room around you is silent. The world outside goes on without you, and that's perfectly normal. Tonight, we'll embark on a journey together, unhurried, without a destination, just coolly, like beams of light drifting between galaxies. We'll leave this planet behind. Not forever, just briefly. We'll drift past the moon, past the planets in our own solar system, to the far edge where the sun's influence mixes with cold, neutral gas. From there, we'll dive among the stars. Not just the nearby ones, but further out, into the vast emptiness of our galaxy, to billions of other suns burning silently in the darkness, each perhaps connected to our own world. Those worlds are called exoplanets, planets orbiting stars other than our own sun. For much of human history, there were times when we didn't know if they were real. The stars were so far away, the planets so small and dark, and our instruments weren't capable of detecting such a subtle shadow. But that has changed in the last few decades. We've built better telescopes. We've designed more sensitive instruments. We've sent observatories into space. We've been able to get a clearer picture because the atmosphere no longer obscures the light. And we've started finding them, first a few, then dozens, then hundreds, and now thousands. To date, we've confirmed the existence of more than 5,000 exoplanets, and astronomers believe there could be hundreds of billions more in our galaxy alone. Hundreds of billions. Let that number linger in your mind for a moment. Each one is a world, each one with its own history, its own chemistry, and its own relationship with the star it orbits. It's possible some of them are unlike anything we can imagine. Others, quietly, might feel somehow familiar. Tonight we'll visit some of them. We have time. We don't need to rush. We'll just float, look, and wonder. How we discovered them before visiting these distant worlds, it's helpful to understand how we found them. Because finding an exoplanet isn't like finding a lost key or a star in the night sky. Planets don't shine with their own light. They are small, dark, and disappear in the brightness of the stars they orbit. Trying to see a planet next to a star from Earth is like trying to see a firefly hopping next to a searchlight several miles away. The firefly is there, but the searchlight makes it impossible to see. So, astronomers have learned to be clever. Instead of directly searching for the planet, they prefer to study its effect on the star. One of the most effective methods is called the transit method. Imagine you are watching a distant light bulb. Now, imagine a tiny moth slowly passing in front of that bulb. For a moment, the light dims slightly, just a tiny bit, for a brief time. If you are watching carefully and your instruments are sensitive enough, you will notice it. You can see a slight dip in the light, and from the size and timing of that dip, you can tell a few things about the planet. How big it is, how fast it's moving, and how often it passes. That's basically what the transit method does. When a planet passes in front of its star, it blocks a small portion of the star's light. If the planet is Jupiter-sized, the dip might be about a percentage. If the planet is Earth-sized, that amount is about 100 times that. A very small dip, almost imperceptible. But our telescopes can measure it. Launched in 2009, the Kepler Space Telescope, focusing on a single patch of sky for 4 years, simultaneously observed more than 150,000 stars, searching for these small dips. It found thousands of planets. Another method is called the radial velocity or Doppler method. This method requires a different kind of subtlety. A star doesn't stay perfectly still as its planet orbits it. By gently pulling the planet onto the star, it causes the star to wobble slightly. When a star wobbles toward us, its light is compressed into slightly shorter wavelengths, shifting very slightly towards blue. When it moves away, its light stretches to longer wavelengths and shifts towards red. By measuring these tiny shifts as few millimeters per second as small as a few millimeters per second, astronomers can detect the presence of a planet and learn about its mass. There are other methods. Gravitational microlensing reveals hidden planets as large objects bend light and pass in front of distant background stars. Not all strange planets are violent. Some are quiet, extremely watery. Now let's sail to a different world, where strangeness lies not in heat and fury, but in depth and stillness. Within the solar system, water is precious and rare on planetary surfaces. Earth has a place that stands out in that it has liquid water covering the majority of its parts, perhaps the only example in our immediate vicinity. Mars has ice, and it may have once had oceans. Jupiter's moons Europa and Ganymede may harbor liquid oceans beneath their icy crusts. But open and extensive surface water is not common there. In the wider galaxy, however, there may be all kinds of planets defined by water. Planets where water exists not as a thin layer on the surface, not as an ocean a few kilometers deep, but as a fundamental element of the planet's structure. Liquid water, a few kilometers deep, or high amounts of ice sheets surrounding a rocky surface, covered by a thick atmosphere of vapor and gas. These superfluous things are sometimes called ocean planets or water worlds. They form from outer, settled structures where water ice is abundant, then they drift toward the interior regions, similar to hot Jupiters, but smaller in structure, in a more dispersed orbit. As they move toward the warmer regions, the ice begins to melt. The result will be a planet where perhaps 10% or more of the total mass is water, compared to Earth, where water makes up less than 1% of the total mass. Kepler 22b is one such candidate. It orbits a star very similar to our Sun, and is located within the habitable zone, where liquid water could theoretically exist on the surface. It is about 2.4 times the radius of Earth. Its composition will remain to be seen. It could be a rocky planet with a thick atmosphere. It could be a gas dwarf like a small Neptune, or it could be a planet entirely covered in water. A planet with a sky beneath a room of vapor and gas, a spherical ocean kilometers or perhaps tens of kilometers deep. Imagine a world where the surface is unfiltered. No land, no continents, islands, rocky coastlines. Its direction, from horizon to edge, is only water. The sky above is pale and covered with thick clouds, its distant, radiant light dispersed, becoming a delicate, fragmented void. The darkness of the ocean below prevents almost any of the light from reaching it. The waves are long and slow, coming from various directions without carrying any particular meaning in a world where land defines a specific direction. Below the surface, the water deepens in a certain way. A diver descending will continue to deepen through cold, dark waters for many kilometers. Pressures constantly increasing, eventually reaching a point where the liquid cannot be contained under immense weight. It will freeze, not into normal ice form, but into high-quality, superior forms of ice that are actually denser than liquid water, namely Ice 5 and Ice 10, forming a giant solid crust around a rocky core. The idea of a world of water is both beautiful and degrading. Life as we know it needs water. But a world entirely covered in water, without rocky shores, mineral-rich river deltas, or sediments carried from eroding mountains, might actually be less conducive to life than we might expect. The chemistry of life might require a mixture of water and rock, the slow erosion of minerals into the sea, the cycling of chemicals between the ocean and the solid ground. A world filled only with water might be too pure, too monotonous, settled into a deep silence. Or perhaps that's not the case. Perhaps our imagination is too narrow. In those deep millimeters of water, in the slow convection currents that carry heat outward from the center, in the chemistry of pressurized water and exotic minerals seeping up from the depths. Perhaps something can awaken there, something we are not currently thinking about or searching for. Drift beneath the oceanic world. Let its gentle waves carry you. Silence your thoughts. There's a kind of planet that wanders alone. No sun, no warmth, no light. Just a world drifting in the cold interstellar space, unbound by any solar system, following the slow gravitational pull of the galaxy. These planets are called rogue planets, free-floating planets, or sometimes nomadic planets. They are thought to be extremely common. Estimates suggest there may be more rogue planets than stars in our galaxy. That's an almost incomprehensible number. Hundreds of billions of lonely worlds rolling silently in the darkness. How does a planet become a rogue planet? It begins within a solar system. In the turbulent beginnings of a young planetary system, as planets form from a disk of gas and dust, their interactions with each other and with the giant gas planets that formed beforehand can be chaotic. Gravitational interactions between two large planets can launch one onto an entirely different path. In some cases, a planet can be ejected entirely from the solar system and travel through interstellar space at enough speed to never return. Some rogue planets can also form from small, isolated clumps of gas and dust that collapse on their own, under their own gravity, instead of a protoplanetary disk. This is the same process that enables star formation, but it stops by refusing to reach the mass necessary for fusion. These objects blur the line between a planet and a failing star.
Gravitational interactions between two large planets can launch one onto an entirely different path. In some cases, a planet can be ejected entirely from the solar system and travel through interstellar space at enough speed to never return. Some rogue planets can also form from small, isolated clumps of gas and dust that collapse on their own, under their own gravity, instead of a protoplanetary disk. This is the same process that enables star formation, but it stops by refusing to reach the mass necessary for fusion. These objects blur the line between a planet and a failing star. When a rogue planet escapes into interstellar space, it is truly alone. The nearest star may be several light years away, effectively infinite for practical purposes. There is no temperature. When its surface is exposed to the very little radiation from the cosmic microwave background and the faint glow of distant galaxies, its temperature approaches absolute zero. Everything freezes. Gases turn to ice. Ice becomes a fragile, dead covering. And here's where it gets interesting. Deep down on a rogue planet, things might be different. Earth itself generates a significant amount of heat internally from the slow decay of radioactive elements and the residual heat of their formation. A rogue planet the size of Earth could retain enough internal heat to maintain a warm interior for billions of years. If it's large enough, it would likely harbor a significant atmosphere filled with hydrogen. Hydrogen is the lightest and most abundant element and can provide good insulation even without sunlight, so the surface might not be as cold as you think. Some researchers have suggested that a rogue planet with a dense hydrogen atmosphere could have surface temperatures above the freezing point of water, even without sunlight. A dense hydrogen shroud could trap internal heat, creating a space in the deeper layers of the atmosphere where liquid water could exist. Not on the surface, because there's no sunlight to create weather there, but deep within the dense, dark, pressurized atmosphere, perhaps somewhere in warmer areas near the surface, pools of liquid water could form. A strange thought. If there is life there, it will exist entirely in darkness, on a world lost among the stars. There will be no seasons, no cycles of light and dark, no connection to any stars, just a faint warmth from the ground, the pressure of a thick atmosphere above, and beyond that, the endless dark space. If you will, there is a poignant solitude of a wandering planet. Perhaps once, it was part of a young solar system, orbiting a star illuminated by light, sharing a sky with other planets. Then it was ejected by a violent gravitational encounter, sent off to float, abandoned to continue in darkness for an eternity. But perhaps solitude is a human concept that doesn't translate well to planetary scale. A wandering planet doesn't long for its sun. It doesn't mourn in exile. It simply, slowly, proudly, indifferently moves through the deep space between the stars, carrying within it its secrets, warm or cold, or somewhere in between. Hold that image in your mind for a few seconds. A world in darkness. Patient, still. One of the most interesting categories of planets discovered in recent years is a type not found in our own solar system. Around us, there are small rocky planets, Mercury, Venus, Earth, Mars, none more than about 1.3 times the size of Earth. Then there are the gas giant planets, Neptune, Uranus, Saturn, Jupiter, which are much larger. There are gaps between them, but in the wider galaxy, we continue to find planets that fit perfectly into that gap. Planets larger than Earth, but smaller than Neptune, somewhere between 1.5 and 4 times the size of Earth. We call these super-Earths, or sometimes mini-Neptunes, depending on their characteristics. Apparently, these are the most common type of planet in the galaxy. It's actually us who are strange, since we don't have such an object in our solar system. Super-Earths are interesting because they are located at a boundary. Their smaller versions, about 1.5 times larger, are usually mostly rocky, like Earth, but larger, with stronger gravity and thicker atmospheres. They can have geologically active surfaces with alternating deep oceans and giant mountain ranges. In some cases, they can be rocky and dry, hot. Their atmospheres are very different from ours. They can be thick, nitrogen-rich, or filled with carbon dioxide or water vapor. Larger super-Earths, approaching Neptune size, are more likely to have thick layers of gas surrounding their rocky or icy cores. Not literally gas giants, just more than rock. The line between a super-Earth and a mini-Neptune is not sharp. It depends on the planet's history, its distance from its star, and how much of its primordial gas shroud it has been able to withstand the effects of starlight. The most studied super-Earth is known as 55 Cancri e. It first orbits its star at an incredible distance, less than Mercury's distance from our Sun, completing a full orbit in less than 18 hours. Its year is shorter than a day on Earth. At this distance, surface temperatures are estimated to be around 2,000 degrees Celsius per day. Initial measurements suggested it might contain a high percentage of carbon, leading to spectacular speculation that its internal structure could be partly diamond, carbon compressed under extreme pressure, leading to the formation of one of the hardest known substances. Subsequent observations further clarified these predictions, but the basic picture remains extraordinary. the rocks themselves, are a world of exotic components, perhaps beyond our wildest imagination. Further away in the constellation Cygnus lies a super-Earth called a Kepler 452b, orbiting a star quite similar to our Sun, but slightly older and brighter. Kepler 452b orbits its star at almost exactly the same distance from Earth as Earth orbits the Sun. Its year is 385 days, just a little longer. It has a radius 60 times larger than Earth's. It also receives slightly more energy from its star than Earth receives from the Sun. When it was announced in 2015, some described Kepler 452b as the most Earth-like exoplanet ever found. Whether this is true depends on how you understand the term Earth-like. We have no information about its structure. We also don't know if it has an atmosphere, oceans, or continents. The 60 times larger radius would likely significantly increase its gravity. If it has a surface, standing there would feel heavier than standing here. If it's rocky, its geology might be more dynamic, more volcanoes, more tectonic activity, more mountain formation and erosion would be visible. However, it orbits a sun-like star at a suitable distance. Its year is almost the same length as ours. It has been in its cycle for about 6 billion years. That's longer than Earth has existed. If it had the conditions for life, that would have been a vast expanse of time for life to begin. Of course, we don't know. And perhaps this uncertainty is a gift of these distant worlds. They lie at the edge of our knowledge, visible enough to make us wonder, but not visible enough to make us certain about anything. They spark the imagination. They make us consider how vast the possibilities are. Slide Kepler 452b in your mind. Perhaps it is a world like ours, older than us, orbiting a silent star in the darkness. 6 billion years of day and night, if any. 6 billion years of seasons it has experienced, weather events occurring on its surface, in its oceans or atmosphere, chemical events in the rock or in the sky. Of all the images science fiction offers us about alien worlds, perhaps the most deeply ingrained is the visual representation of a contrasting sunset. Two suns descending on different horizons, or following each other in slow, intricate curves across the sky, illuminating the clouds with double brilliance, creating double shadows. It's a dream, a beautiful, seemingly impossible dream. And then astronomers discovered them. In 201, the Kepler Space Telescope confirmed Kepler 16b, known as the first planet to orbit two stars. This planet is located in a binary star system about 200 light years away. One of the two stars in this system is slightly smaller than our Sun, and the other is a very small, dim, orange dwarf. While the two stars orbit each 41 days, the planet orbits both at a greater distance, taking 229 days to complete one orbit. From the surface of Kepler 16b, if it has a surface, it's likely a cool Saturn-like gas planet. Two suns will appear as separate objects in the sky, moving relative to each other, sometimes getting closer, sometimes further apart, and sometimes aligning for a double eclipse. Since Kepler 16b, we've discovered numerous planets orbiting binary star systems. These planets have various names, such as Kepler 34b, Kepler 35b, Kepler 47c. Each is a different version of the theme of a world orbiting two suns instead of one. The dynamics of a planet orbiting a binary star are far more complex than those of a planet orbiting a single star. The gravity on the planet is not constant. As the two stars rotate around each other, the gravitational force changes, pulling and rotating. For a planet very close to two stars, these perturbations become severe enough to completely destabilize the orbit. There is an inner boundary, the instability zone. No planet can maintain a stable orbit in this region. The binary planets we found are planets that orbit in dynamic alignment with the binary stars beneath them, slightly beyond this boundary. In such a world, the sky would be extraordinary. If you were standing on the surface of a hypothetical rocky planet with two orbiting suns, like Kepler 34, the two suns might appear close together in the sky at times, almost overlapping, resulting in a bright and sharp display of their combined light. At other times, each would cast its own shadow. You might notice the shadows falling in slightly different directions depending on which one is brighter at that moment. In such a world, sunrise might occur twice, or on certain days it might not occur at all. The geometry of the two orbiting stars makes the combined sunrise and sunset pattern quite irregular. Long periods of brightness could occur, followed by darker days. Transits of one star to another, and intermediate states. The atmosphere on a planet around a binary star system will never look exactly the same. It's important to pause here and marvel at how reality surpasses our imagination. Science fiction imagined double sunsets. Astronomers discovered these double sunsets. Reality goes beyond our expectations, progressing in strange and beautiful ways we can't predict. There are planets far stranger than we imagined in our stories. And they are real. Focus for a moment on that double sunset. As two suns approach the horizon, their light intertwines, their shadows soften. The sky takes on colors that human language hasn't yet named. Despite the diversity and strangeness, underlying our interest in exoplanets is a single question. Could any of these planets harbor life? It's almost too big a question to ask. It touches on a fundamental point about our understanding of ourselves, whether we are alone in this vast, ancient universe. Astronomers use a concept called the habitable zone, sometimes called the Golden Girl zone, when formulating this question. It refers to the range of orbital distances from a star where a planet with a suitable atmosphere could have liquid water on its surface. Not too hot, not too cold. Just right. Water is central to the definition because it's vital to life as we know it. All living things on Earth need liquid water, use it for chemistry, and carry it in their cells. The habitable zone depends on the type of star. For a star similar to our Sun, the habitable zone lies between about 0.9 and 1.5 times the Earth-Sun distance. Earth comfortably sits in the middle of this zone. Mars is on the outer edge, and billions of years ago, when its atmosphere was thicker and its climate warmer, it might have been habitable. Venus is on the inner edge, and its extreme greenhouse effect has turned it into a furnace for smaller, dimmer, and cooler stars, red dwarfs, which make up about 70% of the stars in the universe. The habitable zone is much closer. A planet orbiting a red dwarf in its habitable zone can only orbit a few hundredths of the Earth-Sun distance. This proximity brings its own complexities. The possibility of tidal locking increases. Intense stellar flares can irradiate the planet's surface, and much of the atmosphere may have been destroyed during the star's early, more active phase, leaving no room for life to develop. But red dwarfs are so numerous, and their habitable zones are teeming with planets that they cannot be ignored. Some of the most exciting candidate worlds in our search for life orbit red dwarfs. In 2017, astronomers announced the discovery of 7 Earth-sized planets orbiting a small, cool red dwarf star called TRAPPIST-1. This star is located in the constellation Aquarius, about 39 light-years from us. 3 of these 7 planets, TRAPPIST-1e, TRAPPIST-1f, and TRAPPIST-1g, orbit their star's habitable zone. All 7 planets are comparable in size to Earth. They are also located in an extremely close position. The outermost of the 7 planets is closer than Mercury's orbit around the Sun. The star is so dim that despite their proximity, They receive a similar amount of energy to that received by Earth. The TRAPPIST-1 system generated great excitement in the scientific community and among the public. 7 Earth-sized planets orbiting a single star. 3 of them are in the habitable zone. 39 light-years away, relatively close. Telescopes immediately began a more detailed examination, searching for atmospheric signs and trying to understand the compositions and densities of the planets. What we have learned since then is complex and in some ways disheartening. The TRAPPIST-1 star is a burst star, frequently emitting bursts of energetic radiation and charged particles. The planets are so close to these bursts that this can create significant challenges in protecting their atmospheres and preserving their surface chemistry from damage. Due to tidal locking, each planet likely constantly keeps one face turned towards the star, while the other remains in perpetual darkness, resulting in large temperature differences and creating strong atmospheric flows. But there's another way to think about the TRAPPIST-1 planets, and that requires setting aside the premise that life necessarily has to look like it does on Earth. We don't have any information about whether life needs a specific rotation speed, a specific magnetic field, a specific atmospheric chemistry, or a specific distance from a yellow dwarf star. Life on Earth is the only life we've observed. We have one sample of observation. It would be extremely premature to think that from a single sample we understand all the conditions under which life could arise. We don't know. And that's precisely why this question is so important. Why astronomers continue to study these planets. Launched in late 2021, the James Webb Space Telescope has begun studying the atmospheres of the TRAPPIST-1 planets, searching for chemical traces that indicate whether conditions are suitable for life. We haven't received an answer yet, but perhaps we will. And when it does, whether it tells us the planets are empty and airless or something more interesting, it will be one of the most significant findings in the history of science. For now, let's circle around TRAPPIST-1 in our imaginations and consider what it might mean. A reddish-orange glow in the sky, a star smaller and cooler than our Sun. 7 planets slowly orbiting. And perhaps within that cycle, perhaps the quiet chemistry of life. We've talked about hot Jupiters, water worlds, rogue planets, and candidates for the habitable zone. Now let's take a look at some of the most extreme environments ever discovered. Worlds where physics and chemistry become so unusual that we need to fundamentally rethink what a planet might be. On Neptune and Uranus, under immense pressure in their interiors, scientists believe carbon can undergo an extraordinary transformation between superheated layers of hydrogen and helium under pressure millions of times higher than Earth's atmospheric pressure. Under sufficient pressure, carbon crystallizes. It becomes diamond. And in the extremely compressed, superheated interiors of ice giants, the conditions for diamond crystals to form may be right, and they could rain down like rain, passing through hundreds of kilometers of pressurized liquid and accumulating around the planet's core. This phenomenon, diamond rain, has long been a theoretical idea, but in recent years, laboratory experiments using powerful lasers to recreate the conditions inside ice giants have confirmed that it is possible. Under the right temperature and pressure conditions, carbon dissolved in liquid hydrogens and oxygen forms diamond crystals. They really form. They really fall. Now let's extend this idea to exoplanets. Some of the thousands of worlds we've discovered are massive gas giants orbiting their stars, far hotter and more energetic than our ice giants, with even more extreme internal pressures. In these environments, the accumulation of unusual minerals within planetary interiors may not only be possible, but also continuous. Some researchers speculate that certain carbon-rich gas giants could experience diamond rain on a scale unimaginable in our solar system. There's another type of extreme Earth, lava planets. Some exoplanets orbit their stars so close that their surfaces may be covered in oceans of molten rock due to powerful tidal heating. HD 219134b is a super-Earth orbiting its star just a few million kilometers away, completing its orbit every 3 days. At this distance, the temperature on its surface could be high enough to melt most rock. It's likely to be a lava ocean, not a water ocean. A spherical sea of magma moving and churning under a sky filled with metal vapor and mineral clouds. On such a world, our familiar geological concepts become obsolete. There are no continental plates in the traditional sense, or perhaps the entire surface is a spherical lava ocean, a giant plate constantly mixing and further convectional. There is no water cycle, there is a rock cycle in the most basic sense. Mineral vapors condense in the upper atmosphere, fall to the surface as mineral rain, mix into lava, and eventually evaporate again. Mountains can form and disappear over thousands of years, not millions. The entire surface is in a constant and slow state of change. And then there's the pulsar planet. Pulsars are the remnants of giant stars left behind after supernovae. The interiors of exploding stars emit beams of light like cosmic lighthouses, radiating radio waves into space as they spin at immense speeds. The first exoplanets discovered in 1992, before the famous discovery of 51 Pegasi b, were found orbiting a pulsar. These planets are exposed to intense radiation from the pulsar's rays as they orbit a dead star. Their surfaces will be devoid of atmosphere, scorched by radiation, and battered by charged particles. They are dead worlds in every sense of the word. But there they are, faithfully spinning, orbiting the rotating remnant of a star that died horribly billions of years ago. There's a strange poetry in pulsar planets, worlds that manage to survive a stellar explosion, somehow surviving, or perhaps formed from the debris left after the explosion, and have been orbiting the dead remnant ever since. It reminds us that planets are resilient things. Worlds endure. There's a strange poetry in pulsar planets, worlds that manage to survive a stellar explosion, somehow surviving, or perhaps formed from the debris left after the explosion, and have been orbiting the dead remnant ever since. It reminds us that planets are resilient things. Worlds endure. Even after a cosmic catastrophe, something still remains. Close your eyes for a moment. Imagine those extreme worlds. A rain of diamonds falling through thousands of kilometers of dense gas. A sea of lava swirling beneath a metallic sky. A dead world circling a corpse of a star is spinning in the darkness. Strange? Yes. Seems impossible? Yes. But it's real. Each exoplanet is remarkable in its own right. But what's even more striking, when viewed from a broader perspective, is the extraordinary architectural diversity we find in other solar systems. How planets are arranged around their stars in such different ways. We thought our solar system had a certain structure and that this was normal, perhaps the only possible order. Small stony planets nearby, gas giants far away, everything spread across a wide range of orbits, and the planets move in roughly circular orbits, almost in the same plane. This seems like an orderly structure. It feels like a natural consequence of planet formation. But other solar systems are nothing like this. In some systems, we see giant planets orbiting their stars in very close orbits, at distances where hot Jupiters and warm Saturns coexist, an arrangement completely absent from our solar system. In other systems, small stony planets are arranged in perfect order, their orbital periods aligned by simple ratios, the result of billions of years of slow gravitational interaction, much like harmonious musical notes. The TRAPPIST-1 system is one such example, Its 7 planets form a chain in near resonance. Each planet's orbital period relates to its neighbors in simple integer ratios. This is a dynamically complex system and a balanced structure. The planets attract each other, creating a balance that has evolved into gravitational music over billions of years. Other systems bear the marks of violent pasts. Giant planets orbit in elliptical, inclined orbits that appear to have been flung into their current orbits as a result of past encounters with other planets. In some systems, the planets orbit at quite different angles from the star's equatorial plane. Retrograde hot Jupiters move in orbits opposite to the star's rotation, evidence of its early complex history. All this diversity shows that our solar system is not a template. This is just one of countless possible outcomes. The same laws of physics, with slight differences in initial conditions, a slightly larger disk of gas and dust, a binary star affecting the system from afar, a slightly different mix of elements in the protoplanetary disk, can create solar systems with entirely different appearances. This is a profound thought in itself. We used to think that our solar system had at least a fairly typical order. Now we know that isn't true. It's an ordering of infinite possibilities. And each of these orders is real. Each contains worlds. And each of these worlds has its own story. Somewhere, in a system with no gas giants, just small and large rocky planets, a planet in the habitable zone has never been affected by the gravity of the giant planet. Its orbit has remained stable for billions of years, uninterrupted by anything. The quiet and uninterrupted regularity of such an orbit may have allowed an extraordinary amount of time for life to develop and diversify, if life exists there. Elsewhere, in a system with a gas giant in a distant but slightly inclined orbit, that giant planet may be pumping gravitational energy into the smaller planets inside, triggering volcanic activity in time frames unlike anything in our solar system. The inner planets may be geologically incredibly mobile, constantly renewing their surfaces, undergoing continuous chemical cycles. Each architecture produces different worlds. Each different world is a different experiment in what the universe is capable of. And only in the last few decades have we begun to read the results of these experiments. Take a deep breath. Let the image of these diverse solar systems drift through your inner sky. Consider the countless orders of worlds revolving around countless suns, each one a different kind of possibility. As we float quietly among these distant worlds, it is worth pausing to think about what we are actually looking for when we study them. The scientific answer is information, data, a better understanding of how planets form, how they evolve, how their atmospheres develop, how common the ingredients for life might be. That is the scientific program, and it is noble and important. But there is another level to the question. We are also, at a deeper and perhaps less explicitly acknowledged level, asking whether we are alone. The search for biomarkers, chemical signals that would indicate the presence of life in a planet's atmosphere is one of the most active areas in exoplanet science today. The logic is quite simple. When certain gases coexist in an atmosphere, it's difficult to explain them solely through geological processes. For example, large amounts of oxygen are highly reactive and should rapidly combine with rocks and minerals if something is constantly replenishing it. On Earth, this process occurs through photosynthesis. Life produces oxygen using sunlight. If we find an exoplanet with an oxygen-rich atmosphere, that would be a major clue. More specific gas combinations are even more interesting. Methane and oxygen together are particularly noteworthy. In Earth's atmosphere, methane is produced almost entirely by biological processes, the metabolism of microbes, the digestion of animals, and the decomposition of organic matter. In the presence of oxygen, methane rapidly oxidizes. Significant amounts of these two gases together are not expected in a purely chemically based atmosphere. Finding both on an exoplanet would be a striking anomaly, and this could essentially be explained by the fact that living organisms are constantly producing both. Other potential biomarkers include nitrous oxide, phosphine, which caused considerable controversy when detected in the atmosphere of Venus in recent years, but its interpretation remains debated, and even a biomarker-rich red edge, a distinctive way photosynthetic plants reflect light at certain wavelengths, essentially creating a spectral signature detectable from far distances. The James Webb Space Telescope is searching for these chemical traces by exploring the atmospheres of some exoplanets. It can't yet see Earth-sized planets located in the habitable zones of sun-like stars. These are too small, and their signals too weak, even for the JWST. However, it can study the atmospheres of larger planets and Earth-sized planets around small red dwarf stars. Each observation gives us more information about what planetary atmospheres might look like, while also improving our ability to detect unexpected things. We've come quite far tonight. We've passed by Jupiters scorched by their suns, by the shoreless oceans of the world, and by placeless planets just wandering in the darkness. We glided over seas of lava, imagined a rain of diamonds, and watched two suns set on alien horizons. We pondered life and questioned what it would mean to find it. And now, let us glide more slowly. Let us allow the images to soften and fade. Let us allow the distances to become blurred. We don't have to think of a particular planet. It is enough to feel them together. A vast, silent multitude of worlds surrounding every star we can see, and millions more planets we cannot see. The universe is not empty. It never has been. Even before any eye existed to see it, it was teeming with planets. They were forming, evolving, colliding, migrating, and perhaps in some cases teeming with life, all over billions of years, enough to make any being on any world wonder about their existence. The universe didn't wait for us to begin its work. It always did, and we, on this particular world, around this star, in this particular corner of the galaxy, are a part of it. We are made of the same elements that make up those distant worlds. The carbon in our bodies was created in the hearts of stars. The iron in our blood was released into space during the explosions of these stars, and these explosions filled the galaxy with planets and the raw materials necessary for life, and eventually, curiosity. In a profound sense, we are not separate from distant worlds. We are one with them. The universe, as it looks at itself, is, from a certain angle, astonished by its diversity. It's worth lingering on this thought as your eyes grow heavy and your breath slows. You are part of something unimaginably vast, ancient, and diverse. As astronomer Carl Sagan said, you are made of stardust, and that stardust is the same dust that makes up the worlds we visit tonight. You share a common history with every planet in this galaxy and beyond. The universe is vast, generally silent, full of worlds, some surpassing human imagination, some potentially harboring life, and they are all there, whether we pay attention to them or not. But tonight, we have spoken of them. We have wandered among them a little. We have allowed them to become real in our imaginations. Now, release them. Let the darkness between the stars transform into the faint darkness behind your eyes. Let the planets slowly move away, each beginning to fade as it goes into the distance, until only points of light remain, and then those points too disappear. There's nothing you need to do. There's nowhere to go. Worlds are out there, patient and vast, and they'll still be there when you wake up. The stars are slowly turning. As always, everything is going well. It always has. It will continue long after we are here. And that's not a frightening thought. Not tonight. Tonight, in the silence, only a soft and vast truth. Like the darkness between the stars, like the slow rotation of distant suns, like the patient orbit of a planet in the intergalactic darkness. A truth so vast it is soothing. A universe so full of worlds, with room for everything. You, your breath, the slow approach of sleep. In the deepest sense, we can say that we are not separate from those distant worlds. We are in constant unity with them. We are the universe's own view of itself from a single point, and its wonder at its diversity. A thought worth dwelling on as your eyes grow heavy and your breath slows. You are part of something so vast, ancient, and diverse that you cannot imagine it. As astronomer Carl Sagan said, and you are a piece of stardust. And the stardust within you is the same stardust that makes up those worlds we visit tonight. You have a past with every planet in this galaxy and beyond. The universe is vast, often silent, filled with worlds, some beyond human imagination, some potentially home to lifelike things. All exist, whether we think about them or not. But tonight, we focused on them. We circled them for a while. We made them real in the realm of our imagination. And now, release them. Let the darkness between the stars transform into the soft darkness behind your eyes. Let the planets slowly move away, each fading as they go, becoming mere points of light. And then even those points disappear. There is nothing you need to do. There is nowhere you need to go. The earth is out there, patient and vast, and it will still be there when you wake up. The stars are turning slowly, as always. The planets are in their cycles, as always. The universe, as it always has, continues its work quietly and unhurriedly, as it has for almost 14 billion years. Now you can rest. You can allow your body to be heavy and calm. You can allow your thoughts to thin out, disappear, and stop. Like the morning mist, the universe is vast. You are quite small. In the distance between these two realities, there is a dazzling and astonishing peace. The peace of being a part of something far greater than your own anxieties or unease. The stars don't need your help to keep burning. The planets don't need your intervention to keep turning. And the universe doesn't need your help to keep being vast, strange, and full of the world. Everything goes. It always has. It will continue long after we are no longer here. That's not a frightening thought. Not tonight. Tonight, in the silence, there is only a gentle and immense truth, like the darkness between the stars, like the slow rotation of distant suns, like the patient orbit of a planet wandering in interstellar darkness. A truth so vast it is soothing. There is a universe full of worlds with room for everything, for you, for your breath, and for the slow flow of falling asleep. Good night. Rest well. The worlds are still there.